Hi, everyone. Thanks for joining today's Moldflow webinar. My name is Kristen, and I am going to be moderator for Javier here, who's going to be talking a little bit about cooling methods within Moldflow, specifically going into cool FEM and BAM analyses. And throughout the whole presentation, feel free to ask us questions along the way. We're going to have a series of people in the background here. It's Beth, myself, Jay, and Paul, all on the Moldflow team here to help answer those questions. And then what we'll also do is, like with all the other webinars, we'll go ahead and post this slide deck to the public folder listed there, autodesk.box.com/moldflow20, and it might take a day or two for us to upload it, but you should be able to download that, and then what we'll also do is upload this to YouTube afterwards. And again, there's the question box. Feel free to ask us questions. And just before we get into the good stuff here, just wanted to cover quickly just the webinar series that we hold. If you're not familiar with it, basically it's just a casual talk on some different features that we'd like to share with all the users that, like yourselves. So some of our upcoming topics are a continuation of this presentation, more in depth into the cooling methods of Moldflow Insight, and then also we're going to be working to put together a warpage analysis or warpage webinar on understanding how Moldflow analyzes the warpage and shrinkage in your parts. Past webinars were matching simulation to reality, which is always a good one to refer back to, as well as what's new in Moldflow 2017 R2 release. And if you're ever curious about any of those past ones, like I mentioned before, we do post these to our YouTube channel, so feel free to go to the Autodesk Sim 360 page, and it'll be listed under the Build Your Simulation IQ section there. And if you received this from a colleague of yours, this invite, you can always go to our forums or any of the other options listed there to go ahead and sign up for yourself, and that way it'll be a series listed on your Outlook calendar, and feel free to join the ones that you'd like to attend. And a quick summary, we do have, for those of you who aren't familiar with our knowledge website, we have a website that basically the support team creates and writes articles based on support topics that users like yourselves are coming to us with. So feel free to explore those. A couple of the more recent articles are listed above there. And then you can also go to the Moldflow Insight troubleshooting article page, just with a list of all those articles that we're publishing. And moving on to service packs and hotfixes. So we do like to just remind everyone to try to keep their product up to date. So that's why we always bring that up in these webinars. We do have a service pack for the 2017 release. I believe it's SP2 up to that one. And then we recently released the new Job Manager update. So if you're using the 2017 release, go ahead and check out the Job Manager update listed on the forums, because it could help alleviate or add some new features there for you. And then moving into the R2 release, if you're not familiar with that, the last webinar, Hano, our product manager, actually presented on this. So feel free to take a look at that. We also have a forum post in the forums for it. So you can dive into there, see what the new features are for it. And it is available if you do have the 2017 subscription. You can feel free to go to the Autodesk account under your name, and you should be able to find it there. And moving forward, I'll go ahead and pass it over to Javier, and
Okay.
tell you a little bit about more about cooling.
Sorry. Thanks, Kristen. So, okay, our today's agenda. So it's not much. We have 4 main topics that I would like to cover today. So first, we are going to recap a little bit why we want to do a cooling analysis. What are the goals? What we are searching based on this analysis. The second one is which are the boundary conditions that we are using in our cooling analysis. Much of the settings are defined automatically or by default. Which are those settings and how we could change them. So then on the third part, we are going to take a look on the 2 different cooling analysis that we have based on boundary element methods and finite element methods. And finally, in a live demo, I will import CAD geometry from our mold, from our tool, and we will mesh that and we will take a look on the results. Yeah, the idea of this is to show you that it's not so difficult and maybe you could implement it in your product. Okay, so basics on cooling analysis. So why we want to optimize the cooling? So, well, there are mainly 2 different goals for optimize the cooling. The first of them is to take a look on the quality of the part. Depending on the time that we are cooling a part inside of the tool, we have different surface finishes. So if we are dealing with some crystal-like part, will be not so crystalline, so the crystallinity will be not the expected. And basically because of the time that we are keeping the part inside of the tool, we could have some residual stresses and some thermal bending. And the second main goal why we want to do a cool analysis is because the longer the part is keeping on the tool, the expensive it will be. So we want to minimize or to optimize, better to say, the time that the part is keeping inside of the tool to try to minimize, if possible, the production cost. So, but let's have a look on the energy balance inside of our problem. So we have from one side a melt material that is coming inside of our tool. This melt material is bringing some heat, some energy inside of our system. There is a second way to introduce energy in the system that will be through the cooling lines, because not always we are going to use water at 25 degrees. We could use oil, and probably that will not be on the room temperature. And then we have a flux of energy through the blades based on convection, and once it reaches the surface by radiation with the room temperature. This problem is more complex than that. So the energy balance is not constant through the time. So we could see, or we differentiate 4 different steps through the injection cycle. The first one is the injection time. Usually is the shortest. It's about 1 to 2 seconds. Of course, depends on the volume and the number of cavities that we have in our tool. Then we have a packing time where we are applying some pressure, but usually not introducing more material. And then we have probably the longest So we have a 4th step, which is speed of our machine, how fast we could open the tool and to extract the parts. The 3 first steps is what we call the contact time, and this is what we are simulating in Moldflow. We are not simulating the mold open time. We only add boundary condition, if you want to say that, parameter, how long, or we could let Moldflow to simulate how long should be the time that we need based on some settings for these 3 steps. As you could see here on this small graph, also the temperature is not constant through the different steps. So in the injection time, the surface, the cavity surface is getting warmer, and then it's just decreasing the temperature through the different packing, cooling, and mold open time. This is, we will see in another picture, it's also not so a big jump in the temperature. We are talking about 15 degrees on the surface of the cavity, and during the complete cycle that this could, well, it's mainly depending on the geometry and the volume, but could be in any case about 20-30 seconds, but could be longer, of course. Okay, then let's move to the before Kristen again, because I would like to do a quick poll question to see what are your preferences in the time at the time of choosing a cooling cycle.
Thanks, Javier. Yeah, as Javier mentioned, if you take a look at your screen now, we did launch a poll question for you. Basically, we want to see what cooling analysis type you typically use. We're just curious to see how many people are doing just the base or the default BEM analysis versus FEM, and if you are using FEM, which type of FEM analysis you're using. Thank you all for participating in this. It looks like we're still gathering some results here. And so far, it looks like the BEM analysis is kind of the go-to for most of us. We'll give it another minute here. Okay, let me go ahead and share those results for you all. There we go. So it looks like the majority of you who have answered here have indicated you use the cool BEM analysis, whereas the cool FEM transient with thin cycle is close second to that. And with that, I'll let Javier continue from here. Hopefully we'll teach you a little bit more about those other analysis types.
Okay, thank you, Kristen. Very interesting, the results. So we will discuss maybe a little bit later about this. Let's focus on the boundary conditions. So for showing you which are the different boundary conditions, I create a very simple example, a very simple analysis. This is a disc of 40 millimeters in diameter and 3 millimeters in thickness, and I created 4 trays in a block that should be like 3 times 100. We'll use this basic analysis all over the presentation. So the first boundary conditions that we have, or mainly our boundary conditions, are based on the information that every material has defined it in the material database. So here we could see that on recommended processings, the material provider recommend us a mold surface temperature and a melt temperature. These both temperatures are inside of a range, but this is the mean value. Of course, here in the database we cannot change it. If we want to change that, we need to go to the process settings, and for the cooling analysis we have right at the top the melt temperature, and we could increase or decrease. Then we have the mold open time. As I say, this is just an information for calculating somehow the temperature that is, or the energy that is lost during the opening and closing time. Has no any other influence on our simulation. And here in injection, packing, cooling time, we could define the cycle that we know we want to reach, or we could let Moldflow calculate which is the shortest or which is the cycle time based on some criteria. This criteria, if you click on this button, you open three mainly criteria. The first one is the mold surface temperature, once more taken directly from the material database. The ejection temperature, also again take it directly from the material database. But in this criteria, we could change it and decrease it, for example. And if we decrease it, will be interesting to know, okay, we want to eject the part when reach 100 degrees, but I don't need that everything will be frozen or reach this temperature, and we could just constrain to 90%. More, so we already defined the boundary conditions on the cavity, but the energy flows out from the cavity, and to know how much energy is reaching out, we have this heat transfer coefficient that for the three different stages. We have for filling, packing, and detach. So filling is for the filling stage, packing is for both packing and cooling time, and detach is the time that the mold is opening. Then we have the tool. The tool itself mainly from steel, so we could go to advanced property settings, and we have this mold material, and we could define, or we could change the mold specific heat and the mold thermal conductivity. And once the energy is reaching the surface, we could define which is the ambient or the room temperature. By default, it's always 25, but if it's summer, if it's winter, depending on which is the temperature in your workshop. Then, of course, we have the cooling channels. Here we have two main boundary conditions. First, of course, the inlet temperature, so how cold, which is the temperature of my fluid. And the second one, we could choose here between different options. We see here the combo box. Usually we define the Reynolds number. We know that for a better exchange of energy, we need to reach the turbulence regime. Therefore, we try to reach always this 10,000 Reynolds. But, and based on this Reynolds number, let Moldflow to calculate how much should be the flow rate. But if we have some limitations in our pumping system, we could define the maximum flow rate we have and to let Moldflow calculate which is the Reynolds number to see if we are going to get this turbulent regime. Another settings, another boundary condition that is basic, it's of course the diameter of the channel. But it's also a couple of boundary conditions that usually we don't change and that we could tune for getting a better result. So first is the roughness of the channel. Usually we are drilling these channels, but if we are using another approach, maybe the roughness is different. We have also the transfer effectiveness, so we know that with the time, depending on the coolant that we are using and how we treat this coolant, we know we could have some depositions on the channels that are reducing the effectiveness on the heat transfer. Okay, based on this, let's have a look a little bit deeper on the two different approaches we have in the boundary and in the fillet element methods. So the cool boundary element method was the first method implemented in Moldflow. It's a very nice approach which is working really well for field problems, and our heat problem is a field problem. The main advantage of this method is that we are reducing in one dimension the size of our problem. So we have a 3D problem, our mold, and we are reducing, creating a two-dimensional surface problem. This is reducing the amount of elements that needs to get calculated and doing a very fast calculation. The limitation on this approach is that we could only use a steady state analysis. That means that we use what is called a conduction solver based on the average within cycle temperature. Here we could see in this picture real values. measure directly on the surface of one cavity and 5 millimeters inside of the tool. We could see that on the surface our jump in temperature it's about 15 degrees, but if we go a little bit inside, we just 5 millimeters inside, we see a jump that is not larger than 10 degrees. That makes that this average method is quite reliable, and that give us quite nice and precise results. Okay, so we are talking about a boundary method, so we need a boundary. So probably you know that you don't need to create a boundary to run such a kind of cool analysis, but that you don't create consciously a boundary, it does not mean that the boundary is there. So if you don't define the boundary, Moldflow will define it for you. So in this case, we strongly recommend to create a boundary because, as we saw, there is radiation energy which gets lost on the surfaces of the tool. And if we are doing, or if we let Moldflow to do a larger tool, probably the energy which is lost by radiation will be larger inside of the values that we are dealing with. Therefore, we have a rule of thumb that says if you know the size of your tool, it's okay if you define it 50 millimeters large in every direction. If you define your boundary box, in the log file you will see something like this. You will see that the message saying that we define it the boundary, and in this case, because I know that my tool will be 3 times 100, I define it a boundary which is between 10 and 20 millimeters larger. Usually I define a little bit larger lines for the cooling channels, so I know it's longer, and in this sense the boundary should not cross any beam. So because every beam which is crossing the boundary will not take it into consideration in the analysis. So in this sense I made it 20 millimeters in the x-axis longer and 10 millimeters in the other directions. Also because I know that the part is a little bit shifted to the top, because I will define my fixed half of the tool in 40 millimeters and the bottom in 60 millimeters, I shifted the center of this box. If we don't define that and we let Moldflow to define by default a boundary, we could see that quite larger boundary is defined, and even is of course not knowing that I want to shift the center of the boundary. Probably it's not a big change on this, but we nevertheless strongly recommend to model the boundary. One of the real nice features from the boundary method is that we don't mesh the tool. And because we don't mesh the tool, we are very flexible. In a very flexible way, we could move the cooling channels, and that allow us to optimize based on what if scenarios, what if I move this line a little bit to the top, and to find out how the hotspots, or how we could reduce the amount of hotspots and the temperature on these corners that usually gets a little bit more warmer. Therefore, this boundary method is probably the best method to start a project and to play around with the placing of these cooling channels inside of our tool. Okay, so for the cool finite element method, so of course here we are meshing the tool, and this is bringing us higher accuracy on the temperatures inside of the tool. Because we have different approaches, the time that we need to compute such simulations could increase. As you already know, we have 3 different approaches inside of the finite element method. We have the average within the cycle, so that will be the same kind of calculation that we were using on the boundary element method. Transient within the cycle, In this sense, we will simulate the evolution of the temperatures through the cycle, through these three different steps. And if we are starting from a stop machine and we want to know how many cycles I need to invest to reach the steady cycle regime, I could also let Moldflow to calculate this process. Of course, it's taking a bit more of time because he needs to calculate several iterations through the cycle. In this picture we have here on this slide, we could see as we are increasing the temperature with the different cycles, and as we reach after 8 cycles a steady state cycle. Okay, but the cool finite element method is also the basis for what we could call advanced cooling cycles. First, we could combine this methodology with CFD Conformal Cooling. So you know that nowadays it's possible to, with additive manufacturing, to create very complex cooling scenarios or cooling channels. And these cooling channels could not be modeled by beams. Here is where we could combine the CFD technology with the finite element method on Moldflow. But it's also the base for what I say some advanced cooling cycles, which is the main topic for our next webinar, part 2, which are the rapid heating and cooling processes. In this sense, we are only using steam or water. We could not combine it with oil. I heard some customers that they started to ask about this, but the main reason is that usually the same channel is used for heating and cooling, and if we are using steam, the steam is not cleaning the channel from the previously oil, and if we are using water, the water gets dirty with the oil. So this is something that we are not able to simulate nowadays, but we could combine hot steam and cool water. Also induction heating and hot runner simulation, as we could see in this picture. Okay, and another very nice feature that we have with finite element methods is that we could mesh your tool geometry directly from what you are using in the CAD system. Here we could see a small workflow that we will use for creating such a meshes. So first we will create the mesh of the part itself. Then we will import the hot runners and the cooling channels, and we will mesh that based on beams or 3D. If we are defining some mold inserts, we will need to define or to stick the contact interfaces, and then we could import the mold geometry. First, we create a surface mesh of the mold itself, and in a second step, we create the tetras inside of the tool, and then we could start the simulation. Here I brought you a couple of screenshots from our CAD system, Inventor. Since some releases right now, I could not say if 2009, 2010, we have inside of our Autodesk Inventor Professional and Autodesk Inventor Tool, which contains quite a huge amount of libraries from Hasco and different plates provider, hot runners and things like that. And if we model here, in this case because it's an Autodesk product, we could import it directly to Moldflow. Then we need to define the different properties, we need to mesh, but we could bring such a detailed tool in Moldflow, and probably for the last simulation to let Moldflow calculate the real scenario. Okay, to finish this part, I prepare a comparison between the three methods. From the right hand side, I have this cube, this 3 times 100 that I model with a boundary element mesh. You could see it's a little bit larger because of the boundary approach. In the middle, we have a finite element method based on the conduction solver, so the same that is used on the boundary. And on the left hand side, we have simulation based on the transient within the cycle. You could see like the temperatures are the same in the 3 simulations. We could see maybe that on the boundary is not so sharp the colors around the part, but pretty much the same. And of course, what to say about the transient with cycle, we could see how the different curves, you could see also the different nodes. I just place it from the injection point to the cooling channel, how the temperature is getting smoother and more constant. Also, what I wanted to point out here is how much it took Moldflow to calculate the 3 different simulations. For the boundary, we only needed 12 seconds. For the finite element method with the conduction solver, we needed 35, which is more or less twice. And for the transient within the cycle, we spent about 1 minute. So let's say like 5 times slower than the boundary. This does not mean that always boundary will be faster. Actually, we experience that with finite element methods. When the part is quite complex, we could even be faster with the finite element method on conduction modus compared with a boundary. So more or less will be both of them at the same level. And here's when we start the live demo. So let me change to Moldflow. So where is Moldflow? Here. Okay. So the first of all, as I said, I will import the part that I want to simulate. So I say import, I go up and I have my disk. I say I want a 3D part. Okay, here is my disk, as I say, 40 millimeters, 3 millimeters in thickness. The first thing I'm going to do is to start to mesh this part. Generate mesh. I will define 1.5 millimeters, and I will stop the meshing after the surface meshing. When importing a CAD tool, is really important that all the parts are consistent with the coordinates. So the part should be placed on the cavity space that I have on the mold. If not, I will get some errors. So therefore I stopped the meshing at the surface, because I need one node be placed on the 0, 0 coordinate for modeling my beams for the gate. So to know which is the node which is closer to the 0, 0 coordinate, in this case I will create a local coordinate system. So 0, 0, and in this case, because I wanted to do it on the top surface, is 3. The second point should be a point that will define within the origin our x direction. So in this sense, we could use 1. I usually use 10. And of course, because we want to stay on the same set level, I will say 3. And the third point is the point that will define the y-axis. So in this case, 0, 10, and 3. Here we have. So we know that this node, it's the node which is closer to our origin. So it's the node I will move to the origin. So to do that, I go to Mesh, Move Nodes. I select this node, and I say I want it. I will delete everything. 0, 0, 3. Apply. That's it. So now we could discuss if these two triangles should be merged to this point, or we could leave it like this. Well, in this case, I will leave it like this because I'm going to model with 10 layers, and even if it's not so nice, it will get corrected through the thickness. So I finish with this, so I could go to carry on with my mesh. So with tetras, and I will change it to 10 layers. Mesh now. This should take not so much. Yeah, already started. Okay, here we are. Okay, now that we already have the 3D mesh for our part, I will start creating the hot runner or the gate. I will activate the nodes, and I will go to geometry, and I will create the first line. So we define from, sorry, not this, switch off the visibility. Okay, now start with the line, this one, and I will give in relative, so I know that I want 6 millimeters for the gate. I will define already the property. I will say I want a hot gate. I will not change anything, only the dimensions. I will create a tappet by dimensions. As the starting node is the gate itself, here I will define as 1.5. And here I will define as 6 millimeters pro. Okay, 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 and ready. Sorry, play. Here we have already in red color because it's already has the properties of the hot runner. Okay, then we have already the coordinates from this point. I will give an absolute value because I know that this part is this plate is 40 millimeters, so in this sense 0.040, and I will define another property because this is not anymore a gate. This is hot sprue. Diameter will be 6. Okay, we let all the other things like they are defined by default, and apply, and we have our hot runner. We could switch off. Oh, I created here. Great. So I will go to cut geometry. Yeah, cut geometry. We could create hot runner, and I will select my 2 lines, and I will move it to this layer. So I could just switch off. Correct. Cool. Okay, then I could do the same for the cooling lines, but in this sense I already created a HS file where I draw my lines. In this sense, I go to home and I say add, go up and selecting. We will put all these geometry files on our box, so you could also try to play around with this. Here we have. So now select the 4 lines, and I will add the properties. Yes, this is a channel of 8 millimeters. As I say, I will let the roughness and the effectiveness as 1. Okay, we could see now the lines are blue. Okay, now we could carry on with the meshing. In this sense is curves. Everything is okay. This should be also quite fast. Okay, it seems it's almost done. Okay, here we have. Okay, now that we have all the beams, we need to add the boundary conditions, so the injection point and the flow controller, if you want to call it like that. First, go to injection locations, and we add here on the beam the injection point, and we go to the inlets and we define the same controller for all of them. We could take a look on this, and we see it's 25. I will increase a little bit, and we'll leave it like this. Okay. Okay, now that we have the beams, it's time to import the CAD tool. So I go add again, and in this sense I prepare a mold box based on an inventor file where I define it 2 different bodies. You could, instead of a single geometry file with 2 bodies, you could import the assembly, and inside of the assembly the different parts. In this case, it's a very simple case, and I just did it in one file. Okay, here we have the box. Very nice, everything is matching. So I will change the visibility of these 2 elements, and I will do it transparent. You could see as my part is a little bit shift to the top, included in the fixed half of the tool. We could change here the sequence and say it's a cool fem. One of the things that we need to do now is, as soon as we import this, the properties on this imported tool is part 3D. So we need to select and to assign a new property. So we go to the boundary conditions and we say assign. And we select mold block 3D. Okay, here we don't need to change much. We see that the initial temperature, if in the case that we want to do from production startup, is 40 degrees. And here for this simulation, we could leave it like automatic. But as we will see in the next webinar, if you are doing a rapid heating and cooling analysis, it's important to define the blocks in which side of the tool belongs. Usually, the rapid heating is happening on the fixed part of the tool. And Moldflow needs to know which elements or which blocks are defined on the fixed and on the moving part. So therefore, I'm going to define this as the fixed. As I said, in this case will not be necessary, but I'm just doing fix. Okay, okay. And here the same, if we take a look on the properties, as I said, we import this tool as a part 3D. That's not what we want. So select and assign a new one. In this case, I need to select again a mold block, and I will define it as a moving part. Okay. Cool. Okay. Then that's it. So now it's time to mesh. If we go to the mesh, we see we have a mold mesh tool. We could also click directly here. Because this is taking a while, I will not do it live. And just after the mesh, we run the simulation, and that's it. So I'm going to jump to something that I already prepared for this webinar, and we could take a look on the results. Okay, so I also changed the colors, so just to know, to see easily which is every half of the tool. So let's have a look. So we defined our boundary condition based on a Reynolds number. So we want to know how much pumping flow rate we need. So we could go to the flow rate, and we could see how much is needed. So probably this is not bringing you much because you are also doing all the time. So we have different results that we could take a look on this. One of the plots that usually we don't get, and because we define it move and fix, we have it in this simulation, is the temperature on the partage, on the work plane that is defining the two different moving parts. And we could see how this temperature is defined. Quite nice result that is not possible in boundary element methods, and if we don't define this moving and fix, probably we also not get it here. Another result that is quite nice is the prop plot from the tool. So we could see in red the parts that are not simulated, and we could define some different cross sections, some cuts on our tool to see in a better way our tool. Yeah? So for example, let's do one in the Z direction. In this case, it was for X. I need to define with this unity vector, and for example, clicking here, and we could see the temperature at this level. Pretty nice. Okay. Well, that's it, the live demo. Let's go back to the PowerPoint. Okay, summary. What we saw is that we have two different cooling analyses. The cool boundary element method is a quite flexible and computational light method that allow us in a very flexible way to optimize the cooling analysis, to optimize the placement of these different channels. And the limitation from the other side is that we could only run steady state cool analysis, but this is also not a big limitation because we saw also that the jump in temperature is not so high. It's about 10-15 degrees, depending a little bit of the geometry, of course. From the other side, we have the finite element method for the cooling analysis, and this is a good compromise between speed and accuracy. So if we need more accuracy, but we don't want to, we will need to pay a little bit more of time. We win the fact that we could also calculate some transient analysis. And this is also the basic technology for cooling, for more advanced cooling analysis like rapid heating cooling, or to model the hot runners. And give us also the possibility at the maybe last design step to bring all the tool, to mesh it and to simulate not only the cool, but also probably the warp based on our real tool, or the tool that we will produce after that. And that's it. I don't know, Kristen, if it's any question that is not yet answered, and maybe we could address now.
Hi, Javier. Sure. First of all, thank you for presenting. Great content in there. There was a question that came up from Jose. He asked if there is a way to, when you're working with the full mold design, like the sample one that you had shown in Inventor there, is there a way to make a full section cut of the mesh of it, just to take a look at the mesh of it?
Yeah, well, usually
a little complex there.
Yeah, well, let's see if I understood the question. So, what if we just do planning cutting plane? We could not see the elements inside, but what we could do is to create a new layer and to select a bunch of elements and to move it to this other layer. And then we switch off the visibility on this layer, and we could see what are the elements remaining. And even if it's more than one part, for Moldflow doesn't care in that sense. We could just take away a bunch of elements from different cut parts, let's say like that. I don't know if this is answering.
Yep. Good explanation. Thank you.
Okay, so any other question?
Yep, there was another good one brought up here mentioning or asking if it's necessary to have the runner match to the top of the mold plane there, or the mold plate, rather than extending further out of it. Is it possible to have it a little bit further out, say to simulate the nozzle portion of it?
Yeah, it's possible to leave a gap. So in this sense, I just put it on the same size, but yeah, of course, you could leave a small gap, which is not an empty gap. Yeah, the thing is that for this example, I thought on the nozzle and everything. Well, maybe this was more related to a cool runner, but yeah, so it is not a problem. So we could leave this gap. Actually, I think in one of the slides I show a more advanced modeling with the spiral of the heating system, of the induction heating. We could model like that, and we could mesh it, but this is maybe more related for the next webinar.
Okay, great, thank you. Just taking a look at the additional questions here. Here is one just asking again about the presentation slides. So as a reminder, these slides will be available through the link shown on the bottom of your screen there. They're not up there currently. Just got to do a few minor tweaks to it, but we'll get that up there hopefully by the end of the day today, if not tomorrow morning. But you should be able to download those, as well as, I think, Javier, you mentioned the sample files you'll place up there too?
Yes, the three files, so the part, the tool, and the edges for the cooling. I will place it plus the study I created, so that you just click run and get the results.
Perfect, thank you.
Cool. So then, yeah, thank you for attending this webinar. So we are working on the next one. Hopefully we will be able to do it before Christmas, but if will not be the case, then let's talk next year. Let's see.
Great.
Okay.
Thank you. Thanks, everyone. Have a great rest of your day.